Hello guys, welcome back to another tutorial. Hit the bell icon button so that you don't miss out any tutorial.
My name is Matthew Raymer, and I'm looking forward to guiding you through the virtual jungle, which is recurrent networks. In our previous lesson, we began building on a foundation for discussing recurrent networks by first looking at feed-forward networks. We observed that a feed-forward network has no notion of order in time, and the only input it considers is the current example it has been exposed to. Recurrent networks, on the other hand, take as their input more than just the current input example they are perceiving. They also consider on what they have perceived in recent time spans. The decision which such a recurrent network had reached at time step t1 or t-1 will affect the decision it will reach perhaps just a moment later at time step t. So recurrent networks use two sources of input, the present one and the recent past is the other. These two sources of input combine to determine how such a network responds to subsequent data that comes before it, such as do we in life. Recurrent networks, then, are distinguished from feed-forward networks by that feedback loop connecting up into the mix their past decisions. As it were, they are ingesting their own outputs moment after moment as significant inputs. Imagine the tide coming in at a beach, remembering that unconstrained liquids generally, like seawater, find their own levels. The seawater is the network, and the repetitive incoming waves are the recurrent part of the network. As the seawater encroaches the beach, it is, shall we fantasize a little, learning. It is learning where are those places it can and cannot flow into, and in what quantities and at what speeds. The topography of the beach as the beach is being encroached becomes to the incoming waves fresh data inputted into the network. This topography for this particular occasion of tidal flow is pretty much inert and static data, not changing or moving. Were a volcano erupting, spewing lava down the beach as the tide comes in, the topography of the beach would be clearly in flux and mutating constantly. But no, all is peaceful. The water finds a crevice and forms a rock pool. It finds a channel and forms a runnel into a puddle formed inland a little. It meets a rock and has to go around it if it can, or be repulsed, rebounding up and back upon itself. It meets Billy and Joanne's sand castle and topples it and crashes it down and moves in victorious. Each wave is a new thrust and can be said to contain significant memories of the inflow of former waves on this tide, waves which had proceeded before it. Even though maybe at small scale levels, an amount of water flowed in from each previous wave has found a temporary home on the beach, as it were. Thus, the seawater, as each wave withdraws, is less than came in. It naturally regroups itself and gathers bulk from seawater driving and pulling up behind it. Once replenished, it rallies together to approach again as the next wave. Speaking particularly and minutely, the nitty-gritty of how it regroups and rallies represents change from new learning. In our fantasy, this complex, intricate change in the seawater contains the memories as new learning, which are contributors to every next wave being always unique. Hence, it's often said loosely that recurrent networks have memory, just like we imagined homeopathically incoming seawater on a beach to have. Being able to add this memory to neural networks serves a purpose. Remember, there is new information generated in the course of each sequence itself. The recurrent network uses this new data to perform tasks that are impossible to feed-forward networks. Sequential information is preserved sequentially in the recurrent network's hidden state. This hidden state manages to span many time steps as it cascades forward to redirect the processing of each new example. RNNs are able to find correlations between events separated by many moments. These are called long-term dependencies. They are named such because any event downstream in time necessarily is dependent upon one or more events that came before. Such a downstream in time event is also a function of those earlier events it is necessarily dependent upon. One way to think about RNNs is this: they provide a way to share weights over time. Human memory effuses invisibly throughout a body, affecting our behavior without revealing its full shape. Imagine this as being how information circulates in the hidden states of recurrent networks. The English language is full of words that describe the feedback loops of memory. A person said to be haunted by his past, for example, can be clinically expressed as the consequences that past outputs are wreaking for him in the present time. Now let's look into this enigmatic hidden state. At time step t, it is represented by ht. It is a function of the input that is being processed at the same time step xt, as modified by a weight matrix w, like the one we used for feed-forward nets, and added to the hidden state of the previous time step ht sub 1. Then multiplied by its own hidden state to hidden state matrix U, otherwise known as a transition matrix and similar to a Markov chain. Note, a first-order Markov process, which is related to chains, is a stochastic process which the future state solely depends on the current state only. In probability theory and related fields, a stochastic or random process is a mathematical object usually defined as a family of random variables. Random variables can be associated with or indexed by a set of numbers, usually viewed as points in time, giving the interpretation of a stochastic process representing numerical values of some system randomly changing over time. Stochastic processes are widely used as mathematical models of systems and phenomena that appear to vary in a random manner. When we discuss the first-order Markov process, we often reference it as a Markov process. If it is a discrete space, it is called a Markov chain. The assumption of the Markov process may not be true. But even if it is not true, we can model extra states to make it closer to the Markov process sometimes. In general, the Markov process is a good approximation to solve complex problems in ML or reinforcement learning. If you've done much research on the internet, you've seen Markov chains in action in the form of nonsense pages, which almost make sense, but not quite. These pages are based on analysis of huge numbers of pages through which Markov matrices are built to reconstruct sensible sounding pages. The probability of the transition from one state to another can be packed into a transition matrix. The element position indicated by the pair ij is the probability of transiting from state j to state I. The columns of a Markov matrix add up to 1. The probability of reaching a state from any possible state is 1. Once it is defined as a matrix, we can use linear algebra and eigenvectors to determine its stable state if existing. But let's get back to our discussion of RNNs. The weight matrices are filters that determine how much importance to accord to the present input and to the past hidden state. The error they generate will return via backpropagation and be used to adjust their weights until error does not go any lower. The sum of the weight input added to the hidden state is squashed by the function phi, either a logistic sigmoid function or a hyperbolic tangent. Which one will depend on which is the relevant standard tool for condensing very large or very small values into a logistic space, as well as being the tool for making gradients workable for backpropagation. For as long as memory can persist, and because this feedback loop occurs at every time step in the series, it is the case that each hidden state contains traces not only of the immediately previous hidden state, but also of all those that have preceded h sub t minus 1. Given to process a series of letters, a recurrent network will use the first character to determine its perception of the second character. In such a case, a first letter Q might lead it to infer that the next letter will be U. A first letter T might lead it to infer that the following letter will be H. After all, the purpose of recurrent nets is to accurately classify sequential input. The process relies on the backpropagation of error and gradient descent to do so. Backpropagation in feed-forward networks moves backward from the final error through the outputs, weights, and inputs of each hidden layer. As it goes, it assigns to those weights a portion of responsibility for the error by calculating these weights' partial derivatives, which are the relationships between the rates of change of weights. These derivatives are then used by our learning rule, gradient descent, to adjust the weights up or down, in whichever direction decreases error. Recurrent networks rely on an extension of backpropagation called backpropagation through time, or BPTT. Time duration in this case is simply expressed by a well-defined ordered series of calculations linking one time step to the next. This is everything that backpropagation needs for it to work. Neural networks, whether they are recurrent or not, are simply nested composite functions, such as f of g of h of x. Adding a time element only acts to extend the series of functions for which, using the chain rule, we can calculate derivatives. Truncated BPTT is an approximation of full BPTT, which is preferred for long sequences. This is because full BPTT's forward-backward cost per parameter update becomes very high over a course of many time steps. The downside of truncation is that the gradient can only flow back so far due to truncation. This means the network cannot learn dependencies that are as long as only full BPTT can. Like most neural networks, recurrent networks are now considered elderly. By the early 1990s, the problems arising out of this vanishing gradient had emerged to manifest as a major obstacle to recurrent network performance. The gradient expresses the change of all weights with regard to change in error, just as in a graph a straight line expresses a change in x alongside a change in y. If we fail to be able to know the gradient, we cannot adjust the weights in a direction that will decrease error, and our network ceases to learn. At this point ensues one result, one's output, and if it is not good enough, that's it when using an RNN. Recurrent nets seeking to establish connections between a final input and events many time steps beforehand were innately intrinsically hobbled. This is because with RNNs it is very difficult to know how much importance, weight to adjust, to accord to remoter inputs. The drawback is partially a result of the information flowing through neural nets, being passed through many stages of multiplication. Compound interest allows that any quantity multiplied frequently by an amount slightly greater than one can become immeasurably large. Indeed, That simple mathematical truth underpins network effects. But there is an equal downside to the inverse of multiplying by a quantity less than 1, which is also true. For instance, gamblers go bankrupt fast when they win just 97 cents on every dollar they put into the slots. This is why the layers and time steps of deep neural networks relate to each other through multiplication. Derivatives are susceptible to vanishing or to exploding. Exploding gradients treat every weight as though it were the proverbial butterfly whose flapping wings cause a distant hurricane. Those weights gradients become saturated on the high end, that is, they are presumed by the machine to be too powerful. But exploding gradients can be solved relatively easily because they can be truncated or squashed. Vanishing gradients can become too small for computers to work with or for networks to learn by and are a harder problem to solve. Consider the effects of applying a sigmoid function again and again. The data will become flattened until over large stretches it displays to the machine no detectable slope. This impasse is analogous to a gradient vanishing from a machine's perceptions as it passes through many layers. In the mid-90s, a variation of recurrent net with so-called long short-term memory units, or LSTMs, was proposed. The German researchers Sepp Hochreiter and Jürgen Schebhuber saw this as being a solution to the vanishing gradient problem. LSTMs help preserve the error so that it can be backpropagated through time and layers. By maintaining a more constant error in this way, LSTMs allow recurrent nets to continue to learn over many time steps, over 1,000. Thereby, their advent opened opportunity for a channel for linking causes and effects remotely. This linkage is one of the central challenges to machine learning and AI. This challenge occurs because algorithms are frequently confronted by environments where reward signals are sparse and delayed. LSTMs work by them containing information outside of the normal flow of the recurrent network and in a gated cell. Information can be stored in, written to, or read from such a cell, much like with data in a computer's memory. The cell makes decisions about what is to be stored and when to allow reads, writes, and erasures. This is all accomplished via gates in the cell which open and close. Unlike the digital storage on computers, however, these gates are analog. They are implemented with element-wise multiplication via sigmoids, multiplications, sigmoids, which are all in the range of 0 to 1. Analog has the important advantage over digital of being differentiable and therefore suitable for backpropagation. The cell gates act on the signals they receive, and similar to the neural networks nodes, they block or pass on information. They block or pass based on the strength and import of the information, qualities which they filter using their own sets of weights. Those weights, just as are the weights that modulate input and hidden states, are adjusted via recurrent networks learning process. That is, the gated cells learn when to allow data to enter, to leave, or to be deleted. This is learned through an iterative process of making guesses, backpropagating error, and adjusting weights via gradient descent. That is, the usual ways. Take a look at this diagram. It illustrates how data flows through a gated memory cell and is controlled by its gates. There are a lot of moving parts showing here in the diagram. So if you are new to LSTMs, don't rush this diagram. Contemplate it. Pause the video. Starting from the bottom, the triple arrows are showing the place where information flows into the cell at multiple points. That combination of present input and past cell state is fed not only to the cell itself, but also to each of its three gates. It is these gates which decide how the input will be handled. The black dots are the gates themselves, which determine the fate of the data coming in, respectively whether to let new input in to erase the present cell state and or to let that state impact the network's output at the present time step. S sub C is the current state of the memory cell, and GYN is the current input to it. Remember that each gate can be open or shut, and gates will recombine their open and shut states at each step. The cell can forget its state or not, be written to or not, and be read from or not at each time step, and that variety of flows is represented in the diagram. The large bold letters represent the result of each operation. It's important to note that LSTM's memory cells give different roles to addition and multiplication in regard to the transformation of input. The central plus sign in the diagram is essentially the secret of LSTMs. Stupidly simple as it may seem, this basic change helps LSTMs preserve a constant error when it is one that must be backpropagated at depth. Instead of determining the subsequent cell state by multiplying its current state with new input, the current state and new input are added, and that literally becomes the difference. Note that the forget gate still relies on multiplication, of course. Different sets of weights filter the input to designate either input, output, or forgetting. The forget gate is represented as a linear identity function because when the gate is open, the current state of the memory cell is simply multiplied by 1. This propagates forward one more time step. You may wonder why LSTMs have a forget gate at all when their purpose is to link distant occurrences to a final output. Well, sometimes it's good to forget. If you're analyzing a text corpus and, for example, come to the end of a document, you may have no reason to believe that the document next up will have any relationship to it whatsoever. Therefore, the memory cell should be set to 0 before the net ingests the first element in the next document. In this diagram, you can see the gates at work. Straight lines represent closed gates, blank circles represent open ones. The lines and circles running horizontally along the hidden layer are the forget gates. It should be noted that while feedforward networks map one input to one output, recurrent nets can map one to many. Say one image to many words in a caption, or many to many translation, or many to one classifying a voice. You may also wonder what the precise value is of input gates that protect a memory cell from new data coming in, and which have output gates that prevent input from affecting certain outputs of the RNN. You can think of LSTMs as allowing a neural network to operate on different scales of time at once. Let's take a human life and imagine that we are receiving in a time series various streams of data about that life. Geolocation at each time step is pretty important to the next time step, so that the scale of time is always open to the latest information. Perhaps this human is a diligent citizen who votes every couple years. On democratic time, we would want to pay special attention to what the gal does around election time, and before she returns to making a living and away from larger issues. We would not want to let the constant background noise coming from geolocations affect our political analyses. If this human is also a diligent daughter, then maybe we can construct a familial time that learns patterns in phone calls. Calls which take place regularly every Sunday and spike annually around holiday times. Little that has to do with political cycles or geolocation. Data typically used as input can be like that. Music is polyrhythmic. Text contains recurrent themes at varying intervals. Stock markets and economies experience jitters within longer waves. Each of these operates simultaneously on different timescales that LSTMs are able to capture. A gated recurrent unit, GRU, is basically an LSTM but without an output gate. Therefore, GRUs fully write the contents from their memory cell to the larger net at each time step.
Thank you for watching. Don't forget to subscribe to the channel. If you like the video, do give us a thumbs up and share it. Also check out amazing discounts and offers on our premium courses in the description below.